Hi, and welcome to a lecture on Endfire uniform linear arrays. Here's a picture of the kind of array addressed in this lecture. In this case, we have parallel dipoles numbered n equals 1 through big N, arranged along the z-axis with uniform spacing d. Each dipole is driven by an excitation current I sub n. The primary goal is to select the spacing and the currents to achieve maximum directivity in the plus z direction, as indicated by the yellow arrow. As usual, we'll talk about these antennas as if we were only considering the transmit case, but as usual, the results will also apply to the receive case and with the usual caveats. The purpose for such an array is to achieve high gain in applications where other high gain antennas, such as reflector antenna systems and phased arrays, are not suitable due to considerations such as size, weight, or cost. Although the elements are shown to be dipoles here, in fact, Endfire arrays can be constructed from many types of elements. Other possibilities include loop antennas and monopoles. As we'll see in a moment, the theory presented here applies equally well to arrays comprised of these elements. Examples of elements that would not be suitable for an Endfire array include patch antennas and reflector antennas, for the simple reason that such elements interfere with the radiation from the elements behind it. Here's an outline of this lecture. The first thing I'll do is invoke the principle of pattern multiplication to transform the problem to that of isotropic elements. This will let us do the necessary analysis easily and without becoming encumbered in the details of the specific elements being used. Next, I'll show you two crude methods for selecting spacings and excitations, and show why these methods are not quite what we're looking for. To get something more useful, we'll need to derive the array factor for the isotropic Endfire ULA. From this, we can come up with a design methodology that will yield what we will end up calling the Ordinary Endfire antenna. We'll find that the Ordinary Endfire array, despite having the desired pattern characteristics, does not achieve the maximum possible directivity. We'll talk about how to further increase directivity, and one of those methods will be the famous Hansen-Woodyard strategy. By the way, a good reference for the material I'm covering in this lecture is the antenna textbook by Stutzman and Thiel, and you can find additional details there. Okay, first, let's get rid of the complicating effect of the element patterns. To do this, we invoke the principle of pattern multiplication. That is, the far field pattern of an array can be interpreted as the product of the array factor and the element pattern. The array factor can be interpreted as the pattern of the same array, but with the elements replaced by elements having isotropic patterns. By concentrating on the array factor, we can develop relevant theory and results which will then be applicable to arrays consisting of any suitable element. Okay, here's the first crude attempt to make an Endfire array using isotropic elements. We'll make the excitation currents equal, and we'll make the spacings equal to one wavelength. Thus, radiation from each element traveling to the right will be in phase with the radiation from every other element traveling in that direction. Here's the array factor that you get in that case. In this polar plot, the angle is theta, that is the angle measured from the z-axis, and the distance from the center is the array factor. Here I'm plotting the array factor for an array consisting of just n equals 2 elements. Thus, the maximum possible array factor is 2, and this is indicated as the outer ring of the plot. This result confirms that we in fact have achieved maximum directivity in the desired direction. However, we've achieved the same directivity at plus or minus 90 degrees and also at 180 degrees. The lobe at 180 degrees is labeled the backlobe, and it's easy to see why this lobe occurs. It's simply that the radiation from the elements also adds in phase in that direction. In the vast majority of applications, this backlobe represents wasted power, and we'll probably want to reduce or eliminate that. The lobe at plus or minus 90 degrees is labeled the broadside lobe. This lobe occurs for the same reason. That is, the radiation from the elements adds in phase in those directions. This is always undesirable for an Endfire array, so let's see if we can do something about that first. To get rid of the broadside lobe, we could simply alternate the phases of the excitation currents. For example, if I sub 1 is minus 1, we could make I sub 2 equal plus 1, I sub 3 equal to minus 1 again, and so on. If the number of elements is even, then we would have perfect cancellation in the broadside directions. This works also if the number of elements is odd, but large, since there is one element remaining that doesn't cancel with the other elements in the array, and that remaining element would have a very small effect if the number of elements is very large. To get maximum directivity in the desired Endfire direction, we simply reduce the spacing from one wavelength to 1/2 wavelength. Now the radiation from each element again adds in phase, since the 180 degrees accumulated by traveling the half wavelength to the next element is the same as the 180 degrees resulting from changing the sign of the excitation current. And again, everything adds in phase in the desired direction. When we alternate the sign of the excitation currents and reduce the spacing to 1/2 wavelength, here is the new array factor. As expected, the broadside lobe is now gone. Now note that we have learned an important lesson here. We can mitigate broadside radiation by limiting spaces to be no greater than 1/2 wavelength. This idea will come up again later. Unfortunately, the full-strength backlobe remains. Again, in the vast majority of cases, this would still be unacceptable, and we should try to find a way to reduce that backlobe. In fact, more generally, we would like to know if there's any way to simultaneously maximize radiation in the desired Endfire direction, zero the backlobe, and also reduce radiation in other directions. For that, we are going to need to do a small bit of math. So, we'll derive the array factor. Invoking the far-field parallel rays approximation, the contribution from each element is simply the excitation current times the phase factor that accounts for the geometry of the array. In the exponent of the phase factor, we have beta, the phase propagation constant, which is 2 pi divided by wavelength. So we have beta times the dot product of the element position p sub n, and the unit vector r hat, which points from the origin to the field point. P sub n is simply z hat times n times d. R hat is given in the Cartesian coordinates by the usual expression, which I've shown here. In this case, the dot product is very simple to do, and we simply get n times d times cosine theta. Substituting that into the original expression, we now have the expression for the array factor for this particular geometry and any choice of excitation currents. We can simplify this a little more by requiring the excitation currents to have magnitude equal to 1. That is, we have control over the phases, indicated here as psi sub n, but not the magnitudes. The magnitudes will be fixed at 1. Making this substitution, we obtain the expression on the right. Because we have constrained the current magnitudes to be 1, the maximum magnitude of the array factor is equal to the number of elements in the array. Further, note that this maximum occurs where the exponents, essentially the phases, of each term in the sum are equal. With this expression for the array factor in hand, we can now figure out precisely how to go about designing for Endfire operation with the desired pattern characteristics. First, we'll derive the required excitation phases. For this, we'll enforce the requirement that the maximum value of the array factor occurs in the desired Endfire direction, which is theta equals 0. As we just pointed out in the previous slide, this requires that the exponent in each term of the sum be equal. That is, psi sub n plus n beta d should be equal for all values of n. Thus, we immediately find that the excitation phase of the nth element, that is psi sub n, equals minus n beta d. Substituting this into the expression for the array factor that we developed just moments ago, we obtain the new expression shown here. So, At this point, we have found the phases that maximize radiation in the Endfire direction, and these phases work for any value of the spacing, d. However, we still have the problem of the side lobes and the back lobe to worry about. Since the currents are now completely determined once d, the spacing, is selected, it appears that we have to deal with this remaining problem using only d, that is, by adjusting the spacing. So, let's tackle that. The approach we'll use here is to select d to zero the back lobe, and then we'll see where we stand on control of other lobes in the pattern. So, to do this, we'll enforce a second requirement that the array factor be minimum, and preferably 0, in the back lobe direction, which is theta equals pi. Making that substitution, we see that this means choosing d to minimize the sum shown here. It turns out that making d slightly less than 1/2 wavelength does the trick. Specifically, d is 1/2 wavelength times 1 minus 1 over the number of elements in the array. And choosing d to be this value will completely eliminate the back lobe. Now, how does one derive this solution? The procedure is purely mathematical and frankly a bit tedious, so I prefer not to clutter up this lecture with the details. For those tempted to fill in the gap, and I strongly recommend you attempt to do this, here's a hint. First, show that this sum is 0 if the sum of the phases is equal to an integer multiple of pi. Now you can probably see right away that this is true for a 2-element array. For example, if you choose 2 beta d to be equal to 0 and 4 beta d to be equal to pi, that causes the sum to be 0, and the sum of 2 beta d and 4 beta d turns out to be pi, just like I suggested. Now, if you take that piece of information and you also require d to be less than or equal to 1/2 wavelength, then you'll get the result that I've shown here. The advantage of choosing the solution that yields d less than 1/2 wavelength is that it precludes the possibility of side lobes being as strong as the main lobe, as we saw earlier in this lecture. So, we now have essentially everything we asked for. That is, maximum radiation in the desired Endfire direction, 0 back lobe, and side lobes which are not necessarily minimized, but are at least not full strength as they are in our earlier Crude solution. To demonstrate the features of this design method, let's look at a 2-element array. Following the procedure we just developed, we find the element spacing for a 2-element array is 1/4 wavelength. And the phase shift, that is the psi sub n's, are different by pi over 2 radians. That is 90 degrees. Shown here is a plot of the resulting array factor. As expected, the maximum array factor is 2 in the desired Endfire direction, and the array factor is 0 in the opposite direction. This particular pattern is referred to as a cardioid, literally meaning heart-shaped. Since this array has 2 elements, it does not improve the gain by much over what is already provided by the elements. However, this particular design, that is the design yielding a cardioid pattern, has another application, and that is direction finding. Direction finding is a receive mode application. The idea is that there is only one null in this pattern, and that null is very narrow. So what you can do is spin the array in azimuth until the signal disappears. At that orientation, you know the null is in the direction from which the signal is arriving. Now, you could also spin the array until the magnitude of the received signal is maximized. However, this is much less accurate because the main lobe is very broad. In fact, for the signal maximization approach to outperform the null finding approach requires a very large array. So, if you have only 2 elements, null finding with the cardioid pattern turns out to be the way to go. Here's a result for 3 elements. Here the maximum array factor is 3 in the desired Endfire direction, and the array factor is 0 in the opposite direction, so all is expected. Also worth noting here is that the main lobe shape is getting narrower, as you might expect. Here's a result for 10 elements. Here the maximum array factor is equal to 10 in the desired Endfire direction, and the array factor is once again 0 in the opposite direction, all as expected. And the main lobe continues to get narrower, again as expected. Up to this point, we have been limiting our attention to the array factor. And of course, this is the array pattern only if the elements are isotropic. And of course, practical antenna elements can't be isotropic. So, to go further, and specifically to compute directivity, we need to account for the actual element patterns. This, of course, is very easy to do as long as the principle of pattern multiplication applies, since then the pattern is proportional to the product of the array factor and the element pattern. And that will be valid as long as we can assume that mutual coupling is negligible, which is often, not always, but often the case. Once we have the actual array pattern, then we can calculate the directivity using any of the usual methods. For example, computing the normalized pattern, integrating over that to get the beam solid angle, and then dividing that into 4 pi steradians to get the directivity. Antenna textbooks, such as the one referenced at the beginning of this lecture, typically compile results for various numbers and types of elements. Although you actually need to do the calculation to get accurate numbers, the results can generally and approximately be characterized as follows. The directivity of the ordinary Endfire array, as specified here, is approximately twice that of the same array, with excitations modified to steer the main lobe to broadside as opposed to Endfire. So, for example, if you find you get a directivity of x for a particular uniform linear array of isotropic elements with the ordinary Endfire spacing described here, but instead scan to broadside, then the directivity will typically be about 2x once you change the phases to scan to Endfire. Now be careful, that rule of thumb applies only if the elements are isotropic. However, that's a pretty good starting point for understanding the difference between Endfire and broadside pointing arrays. And, I repeat, just to be clear, to get an accurate value for the directivity of a practical array, you will typically need to figure out the actual normalized pattern and then integrate over that to get the directivity. In other words, you have to account for the elements. Now, recall that the ordinary Endfire antenna merely maximizes the radiated field in the Endfire direction, so we end up with the largest pattern magnitude in that direction. This is not quite the same as maximizing overall directivity. Now that may seem counterintuitive, but just remember, directivity depends on the entire pattern, not merely on the value of the pattern in a particular direction. So this begs the question, if we want to increase directivity and not merely maximize radiated field magnitude in a particular direction, then what should we do? Well, there are actually multiple ways to accomplish this, but here we'll limit ourselves to the most popular one. We can increase directivity by slightly reducing the element spacings and then slightly increasing the amount by which the excitation phase changes from element to element. The amount by which we'll reduce the spacing from the value for the ordinary Endfire design typically depends on what we are willing to tolerate for a backlobe, and I'll show an example of that in a moment. The amount by which we increase the element-to-element phase shift is identified on this slide as delta. A number of possible values for delta exist. The most common value is pi divided by the number of elements in the array. This is known as the Hansen-Woodyard criterion. Another somewhat less well-known value of delta is 2.92 divided by n, which is known to maximize directivity for a particular spacing. Now, the latter might seem like the obvious way to go, but in practice it is typically not. First, the difference between pi and 2.92 is not so great. Second, everything we do here to increase directivity is going to compromise some other characteristic of the design. More on that later. Suffice it to say, the Hansen-Woodyard value is usually the way to go. Okay, so where does this come from? Now that's a long story and requires a relatively deep dive into some relatively arcane mathematics. If you'd like to follow up on that, the textbook reference at the beginning of this lecture would be a good start. For this lecture, I'll simply state this result and then show you how it works. Just as for the ordinary Endfire array, I will not try to summarize the directivity of all possible enhanced designs, but rather I'll simply suggest the textbook if you want to see a lot of different results. What I will say is that the directivity of these enhanced designs is typically a little less than twice what you would get for an ordinary Endfire array. This is attributable primarily to narrowing of the main lobe, as we'll see in a moment. So, if directivity is your primary concern, then the Hansen-Woodyard approach, or one of the related schemes, is probably the way to go. This brings us to the entrance of what I like to think of as the Endfire array rabbit hole. What we have at this point is the ordinary Endfire array, which is simple, but does not yield the maximum possible directivity. And then we have a whole class of alternatives to the ordinary Endfire array that yield better directivity, but for the latter we have no specific rules about how precisely to set either the spacing or the excitation phases. And there are consequences to increasing the directivity in that manner. The first thing you have to realize is that the backlobe will typically not be 0 unless you deliberately tune the design for this. Now, this is not such a big deal, as I will show by example in a moment. The second thing you have to realize is that side lobe levels can increase when you use Hansen-Woodyard or some other approach. So, if you have a specification on side lobe levels, you will have to check for this separately. Third, these increased directivity designs tend to have reduced bandwidth relative to the ordinary Endfire array. So once again, if you have a specification for bandwidth, you're going to need to check for that separately. Here's an example of what's going on with these types of designs. On the left is a 10-element ordinary Endfire array, in fact the one I showed earlier. The spacing for that array is 0.45 wavelengths. In the middle, we have the same array, but now using the Hansen-Woodyard excitation phases. The spacing in this case is on the very edge of what is allowed, since the Hansen-Woodyard criteria require that the spacings be less than those of the ordinary Endfire case. However, with this in mind, note that three things have happened. First, the maximum array factor is much less than what we achieve for the ordinary Endfire. It seems like this should mess up performance, but then we notice the second thing. The main lobe is much narrower. So something good is happening here. The third thing we notice is that we have a strong backlobe, which again is almost always undesirable. Now, we can take care of the backlobe by reducing the spacing, as is technically required for the Hansen-Woodyard design. In this case, we find that reducing the spacing to about 0.37 wavelengths completely eliminates the backlobe, as well as reducing some of the far out side lobes. Now keep in mind that when we reduce the spacing, the excitation phases have to be recomputed, and this has been done. So, comparing the ordinary Endfire to the Hansen-Woodyard with spacing set to eliminate the backlobe, we see that the maximum array factor has decreased, but that is irrelevant. What is relevant is that the main lobe is significantly more narrow, and as a result, the directivity is much greater. Further analysis would be required to determine precisely how we came out in terms of side lobe levels and bandwidth. Okay, so let's wrap this up. We've worked out the ordinary Endfire design procedure, which maximizes the array factor in the Endfire direction and zeroes the backlobe. Along the way, we encountered the 2-element ordinary Endfire array, which has a cardioid pattern, and I pointed out that the utility of that particular design is in direction finding. We then addressed the broad class of designs, including Hansen-Woodyard, that increase directivity over what is possible with the ordinary Endfire design. But there's no free lunch, and you need to consider what happens to the backlobe level, the side lobe levels, and the bandwidth when you use one of these enhanced directivity design approaches. Finally, let me point out some pitfalls that are commonly encountered when dealing with Endfire arrays. First, do not forget that you must include the element pattern in order to know precisely the directivity, side lobe levels, etc. You can't simply design assuming isotropic elements and assume that things will work fine after you introduce the actual element patterns. Second, let me remind you that pattern multiplication depends on the mutual coupling being negligible, and this may not necessarily be the case for your application. This is true especially for Hansen-Woodyard arrays, since the required spacings are often much less than 1/2 wavelength. Third, remember that you have to feed these elements somehow. If you plan on having a single input and output to the antenna, then that feed system is going to be pretty complicated for any array having more than 2 elements. Now, there's actually a common workaround for all 3 of these pitfalls. That workaround is called the Yagi. In a Yagi antenna, you only need to feed 1 element, and the others are fed by mutual coupling. This simplifies the overall mechanical structure of the antenna, but of course greatly complicates the analysis and design of the antenna. That, for sure, is a topic we must defer for another lecture. And with that, we conclude this lecture on Endfire uniform linear arrays.